Right, ladies and gents. So your paper was based on a 2018 one. Just wanted to say well done to all the people that are putting in a lot of hard work. I can see that there's definitely been preparation and revision done from a huge amount of you. Because even when answers aren't getting answered quite correct, you are talking about stuff that we've learned in lessons that you must have picked up in revision guides. I can see that there has been preparation and hard work done in, and I appreciate that. So start off with a thank you. I'm pretty proud of where we are. We've got some fantastic scores. And you got to remember on a higher tier, if you get 50% of stuff correct, you are doing a really, really good job. And that's at the end of year 11. Half of the country can't get a grade 4 in science, and pretty much every one of us in here stands a really, really good chance of getting a 4 at least, let alone, obviously we've got some people with really high targets. So keep it up and don't get disheartened by any percentages. You will get lower percentages in science than you will in other subjects. That's pretty common. Right. I'll rattle through and I'll explain the ones that need explaining. Pause the video whenever you want and look at the mark scheme. Just make the mark scheme a bit bigger for you. There we go. Right, 1.1. Anything that can react with an acid apart from a metal oxide. So don't name a metal oxide. And then you got the list here: metals like sodium, or a metal oxide, hydroxide like sodium hydroxide, or a carbonate like sodium carbonate, or an alkali. The formula for calcium nitrate, because we've got calcium with a 2+ charge and nitrate ions with a minus charge, we're going to need 2 of the nitrate ions to balance out the 2+ from the calcium. So you put brackets round that NO3 ion itself, lose the charge, put a subscript 2 next to it. For 1.3, lots of really good answers. The most common reason for not getting 6 is for not telling us how to make magnesium sulfate itself. So the oxide you need is magnesium oxide, and the dilute acid you need is sulfuric acid, which you'd mix together, warm and stir to speed up the reaction. Keep adding the magnesium oxide until it's in excess, until the powder sinks to the bottom and doesn't react, giving it enough time to react. You don't need all of these bullet points, but it does help to pick off as many as you can. You'd then filter it, leave the solid magnesium oxide in the top of the filter, and then you would take the filtrate that's at the bottom. And most of you said that you were going to be putting it on a windowsill or something like that in a petri dish or something. Some people were talking about using a Bunsen burner or a steam bath to evaporate the water and crystallise it. Good work. Don't spend long on that. This one here, the ratio is 1 black dot to every 2 grey dots. That is 1 iron to 2 sulfurs. Make sure you have capital letters, lower cases, and subscript 2s as the mark scheme shows over here for me. For the iron, protons is the atomic number down here. That's the proton number, 26. If you've got 26 protons, positive protons, you'll have 26 negative electrons. In an element, obviously, if it's a compound or something like that, you can gain or lose electrons, so that can vary. That's why it's called a proton number, not a proton and an electron number. For the neutrons, total mass is 56, the mass number, which means that if we subtract our 26 protons from it, we'd have 30 left over to be the neutrons, remembering that electrons weigh virtually nothing in comparison. For 2.3, we're looking at properties here. So if you talked about anything about atomic structure and electrons, that's where you went wrong. Even though it was good chemistry knowledge, it does not answer the question. So what we want from things is comparatives like higher melting points, more dense, so the iron here, harder, stronger, less reactive, forms different charged ions or coloured compounds, or can be a catalyst. Those last 3 are specific to transition metals. Okay. A few people were saying that sodium would conduct electricity. It's metal, it would conduct electricity. It'd just be a really stupid idea to make wires and stuff out of it because of the danger that could be associated with a highly reactive metal. 2.4, this is a Kim-Kanye equation. So you need to say, first of all, that carbon is more reactive than nickel. Remember we said if it's not an ion, like aluminium or sodium, then carbon will be able to displace it. So carbon is more reactive than nickel and will displace the nickel from the oxide or take the oxygen. Okay, a few different ways you can say that. Feel free to pause and look at the mark scheme. First little bit of maths, scarier than it looks. Atom economy is asking you what percentage of the atoms were useful products. So here there's nickel is what we're using, and that's 59. out of a total of the nickel, carbon, and oxygen added together. So the total mass of stuff that you were making was all those added together, which is the nickel, carbon, and oxygen, which is 87, first mark. And nickel represented 59 out of the 87. To turn it into a percentage, you'd do times it by 100. If you quickly worked out the wrong MR, you can still get a mark for this. And it should give you 67.8 if you did it to 3 significant figures. If you didn't, you can still get 2 marks. And for question 3, we did this one, didn't we? No, we didn't do question 3. We skipped question 3. Didn't cover that content before the test, so we didn't give you that one. Number 4. So this is asking about the history of the atom. So I'll just run through what each one is supposed to be here, and that'll give the answers to 1, 2, and 3. So D is John Dalton's atom. He revised Democritus's idea of an atom being the smallest individual particles, and he was comparing them to billiard balls. Then came J.J. Thomson, who discovered the electron, which came to this, where his plum pudding model was like a positive sponge with negative electron plums dotted around inside it. E is very, very similar, but just a red herring. It's not, doesn't fit into our pattern. After that, you had Rutherford, Marsden, and Geiger, who were looking at the alpha scattering investigation, which you do in more detail in physics, which led to the conclusion that there is a central dense nucleus with mainly empty space around it. And then you got to Bohr, who put those electrons in discrete or separate energy levels, you know, the 288 stuff. So in order, plum pudding model should be B, and the alpha particle one was C, and then Bohr's work was A, and A and C were most commonly mixed up between question 2 and 3. I can understand that. They're both the nuclear model. For 4.4, which is your... I'm not keeping up here with my mark scheme, I do apologise. Yeah. So mass number is the protons and the neutrons added together. For 4.5, it's asking for an estimate. You could work it out. You could find out 60% of 69 and 40% of 71 and add them together and get the actual correct number. But it's relying on the fact that you should know that 69 and 71 halfway in between is 70. So if it's 50-50, then the average would be 70. There's more of the 69, so it's going to be closer to 69 than 71. So it's going to be just under 70, okay, which is going to be the second box down. For 4.6, so in the first diagram, this one here, you notice that there's neutrons here and there's not here. That's because they didn't know about neutrons when they did the alpha particle investigation. So I remember when this came out in the exam series that the pupils were confused because they thought they were asking for how Chadwick discovered neutrons for the experimental evidence. It's not what it's asking. It's just what you need to know. Chadwick discovered neutrons. First mark. And then why that was linked to isotopes, and that is just regurgitating the stock 2-mark definition for isotopes. Isotopes have the same number of protons and a different number of neutrons, or said in a slightly different way, they have the same atomic number but a different mass number. It's quite common for people to lose marks on that bit, or to get a couple of them mixed around in the first bit. Right, plotting the graph. You didn't have to do this one because it... Just check. Yeah, this question wasn't on your paper, so it'd be silly to go through that one. It's not like that I just recorded this video a minute ago, but it didn't record, and then I did this and did that question, and yeah, that's exactly what happened. But here I am recording it again. It's working this time, I hope. So question 6 for me, question 4 for you, I think. Why electrolysis would not take place? Most of you spotted that this is solid zinc chloride, and you would need it to be liquid or molten or dissolved. First mark. It's an explain question, so you need to say why it needs to be like that. So you'd either say that in a solution, when it's dissolved or when it's molten, the ions are free to move and carry the charge. You have to say ions there. You can't say atoms, particles, whatever it is, and it's not electrons that are flowing, so you have to say ions. Or you could say in solids that the ions are held in place and aren't able to move. Whenever it's electrolysis, get it into your head, we need to talk about ions. 6.2 has got a similar theme in that it's asking why graphite conducts electricity. So graphite is one of the 2 types of allotropes of carbon you should know about. So we've got graphite and diamond. So you should know that graphite has got 3 covalent bonds. whereas it could potentially make 4. So it has 1 electron that is delocalized or free. So the first mark is for the 3 bonds, and the second mark is for saying it has a delocalized electron. And the commonly missed third mark is for saying that those electrons can flow through that structure and carry the charge. What it can't do is jump between layers. So electricity doesn't like to jump between gaps. So when you hold 2 metal wires with a gap in between, it doesn't flow in between the same way. When you have the layers of graphite, it doesn't like to jump between the layers. Big enough voltage it would, but that's not what the question's looking at. On this question here, it relies on you reading the first statement. So I'm just going to read that out to you. The student investigated how the volume of gases produced changes with time. He's got a good way of measuring the time there, but he's got a pants way of measuring the volume. I can estimate that there's twice as much hydrogen as chlorine, but I don't know what the volume is. So the 2 marks are for saying how you would measure the volume and why that change was needed. So you could use measuring cylinders, which have got graduations down the side, burettes, which we've used in titrations, gas syringes, which we will be using in rates of reaction. Hoffman voltammeters are the really delicate glass things that I said, why do you think we don't use these when we're looking at electrolysis? And I think Zach said, oh, because we'd probably break them. And I'm like, yeah, you're absolutely bang on. So the 2 marks, use something which you can measure, like a measuring cylinder, because test tubes can't. Okay, you could even get away with drawing graduations on a test tube. 6.4, if you need, pause and look at the options here. Describing graphs is a weak area for many pupils, and it is well worth your time to look at this, because you can take lessons from this and you can apply this to a range of other circumstances. So, hydrogen is directly proportional. This means that it starts off at 0, 0, the origin. So if it's proportional, it can have a y equals mx plus c with a c-intercept. If it's directly proportional, it's just a y equals mx graph. So proportional means it's going to have a positive correlation. Directly proportional is a positive correlation that goes to the origin. Inversely proportional is the line would start higher and go lower. So as one factor gets higher, the other one gets lower, and vice versa. You could calculate the rate of the reaction, which would be quite good. So a number of people did that. You might not have done it in 0.45 centimeters per minute, but you did something similar, so you can get credit for that too. Talking about the chlorine is not directly proportional because although it starts off at the 0, 0, the straight line doesn't. So you'd say for the first 8 minutes, it is increasing at an increasing rate. So when you have a curved line, it's going up, but it's also the rate is changing too. So it's increasing at an increasing rate. Funny when you say it like that, I know, which is why a lot of people miss a mark like that in exams. And then after 8 minutes, it is proportional, and you can get a mark for saying that it's going at the same rate as the hydrogen, or the 0.45 centimeters cubed. Okay. For number 6.5 or 4.5, I think for you, gas isn't escaping, and you've got the same moles of gas, which means you should have the same amount. Avogadro said if you've got 1 mole of any amount of gas, that should be 24 litres. That's the next question. So where is the hydrogen going? You might remember when we did about electrolysis, talked about it being a chemical weapon and that it dissolves in eyes and lungs to make hydrochloric acid. It dissolves. So it dissolves or reacts in the water to form hydrochloric acid. Common place to lose marks because it's not absolutely obvious from the question, but you might now remember it. Maybe not. Who cares? It's 1 mark. 6.6. We're calculating the moles of chlorine collected after 20 minutes. So let's just go back up. 20 minutes, go up to chlorine. It's 3 squares up. Oh, it's not going to be each square is worth 1. It's not going to be 6.3. It's going to be 6.6. Looking at scale. So we've got 6.6 centimeters cubed. And we know that 1 mole would be equal to 24 decimeters cubed. Let's change our 6.6 centimeters cubed into decimeters to get 0.0066 like this here in the marks. Okay, so if 24 is what 1 mole is, then having 0.0066 means we've got a lot less than 1 mole. So we can compare that. How many? We get the 0.0066 divided by 24. We can find out how many fractions of a mole it is, and it is it's 2.75 times 10 to the minus 4 because it asks for it in standard form. Which is 0.000275. Tricky question, quite easy to lose marks, but you can get that mark from reading off the graph, and you can get 33% of that question. Number 7. Common mistakes on this one is a displacement reaction, so people mentioned potassium chloride and forgot iodine. Or they did something like chloride iodide or something like that. Couple of little points. If you say potassium chloride, it's an ide because it's a compound with an ion in it, and iodine, because iodine is the element, iodide would not be correct. For 7.2, that theme carries forward. It's in the mark scheme here that it says that if you talk about iodides instead of enes, then you won't get the mark. So this is not about the size of the atom just because of the size, it's because of the electrons. So I'm going to talk about chlorine. You can flip everything I'm saying and say the opposite for iodine. So chlorine has got its outer electrons closer to its nucleus because it's got less energy levels or less orbitals or less shells. That means that there is a stronger attraction between the positive nucleus and the negative electrons because they're closer together, just like when you bring magnets closer together, it's a stronger attraction. And that means it's easier for chlorine to stick that extra electron on that it needs to go from 7 electrons in its outer shell to 8 electrons in its outer shell. Most people have the right idea for that, even if you didn't get the marks because you were talking about the size of the atom. 7.3, hydrogen chloride, hydrogen, non-metal, chlorine, non-metal. So this is a non-metal, this must be covalent bonding. And it's a gas at room temperature, so we're talking simple covalent bonding. The first thing would be identifying the type of bonding, simple molecular or simple covalent bonding, first mark, and then explaining why they're generally gases at room temperature as a pattern. So not just this one, but even things like oxygen and nitrogen and things like that. So despite them having strong covalent bonds holding the two atoms together, in between the different molecules there are weak intermolecular forces, weak forces, and that we need very small amounts of energy to overcome. And notice it says little energy to overcome those rather than temperature. We're talking about energy here. Okay. Just say there, don't talk about bonds breaking. We're not breaking the covalent bond for the hydrogen chloride apart. We're breaking the forces that are holding them together. Oh, sure. I've done it again. I've started answering a question for one that you've not done on your paper. All right, well, that was question 7, and you didn't do question 7. So, apologies. You've probably already put your hand up in class and told me that you didn't do this, and I've already told you to go on to the next one. Soz. I did that last time. Oh well. I probably can't be bothered going back and editing the video. 8.1 suggests one hazard associated with step 1. There's a few things here, but some of the obvious ones are using chlorine, which was discussed being a chemical weapon. So chlorine is toxic. You can't just say there is chlorine, you have to say what the hazard is. Same thing with this, carbon monoxide is toxic. Okay? We're looking for the right keywords here. So not deadly, not dangerous, we're looking for toxic. Skull and crossbones symbol. 8.2. You have one reason why it would be hazardous for water to come into contact with sodium. The most annoying bit for a lot of you is probably going to be ignore vigorous, allow violent. So vigorous or reactive is not dangerous enough in terms of vocabulary, whereas explosive or violent is. Hope you see the difference there. Sodium hydroxide produced when a sodium reacts with water, like any alkaline metal. It produces a strong alkali, which is corrosive, and it also fizzes and produces hydrogen, which can set on fire, like when potassium goes in water, which is potentially a dangerous fire. 8.3. As soon as you see that it's taking place in argon, we should think, well, argon is a noble gas, so we need to say that it's inert or unreactive for the first mark. And it says why relating to the air, what's in the air, so we have to say what's in the air. So it's not going to react with oxygen from the air, or it's not going to react with water from the air. Okay, most people are talking about oxygen. Good. Just with the air, not specific enough. Hopefully you can see why. 8.4. So why would we not expect titanium chloride to be a liquid at room temperature? 2 avenues to explore for this, quite interesting. Most people are going to go down the ionic avenue, so let's talk about that first of all. Titanium, metal, chlorine, non-metal. So that would be positive and negative ions gaining and losing electrons forming an ionic bond. So spotting it should be ionic, 1 mark. Then knowing that you'd form an ionic lattice with lots of pluses and minuses, that would be strong bonds, strong electrostatic forces, that'd be another mark. And then saying that that would have a high melting and boiling point because it would take lots of energy to overcome that, that'd be 3 marks. You could go the other way though. You could say, well, if it is a liquid at room temperature, it might be behaving like a simple molecular structure, simple molecule, like the previous answer in 8 point, what was that one? Oh no, the other question, probably 6 point something now. And you could say that it's probably got weak forces in between its molecules, and that it's easy to overcome those. And that metal chlorides are usually ionic. Most people didn't go that big. Most people talked about it being ionic. So well. 8.5. Sodium atoms are oxidized. Why is this an oxidation reaction? It's not because oxygen's added, which it was on the foundations here, because, oops, scroll too far, because if we look at it here, the sodium has not got any oxygen in the equation at all. Okay, so we look at it in the other terms. Oxidation is loss, reduction is gain, oil rig. So oxidation is loss of electrons. Sodium loses electrons. I know half equations for 8.6 or 6.6 for you look scary, but we just said what's going to happen. Sodium, group 1, 1 electron in its outer shell, it's going to lose an electron. Okay, so we're going to have a sodium ion, Na+, and the electron that it's lost, E-. For number 7, the easiest mark here is for getting the MR for titanium chloride. So if you got 190 in there by getting the titanium, chlorine, and adding them all up, then you got one of the marks available. And to be honest, if you didn't know what's going on, that's a nice, easy one to get 4 marks. Okay. Feel free to pause and read the rest of the instructions here, because there's several ways that you can do this. One of them, where you're getting these 20,000 and 40,000, is because you've got the 40 kilograms and converted it into grams, because the formula we use relies on grams. But I'll tell you what most people did, because it fit with how it was taught by me, and it got you the right answer. Okay, so most people got the titanium chloride and got 40 grams and divided it by 190 and got 0.211. And then a lot of people got the 20 grams and divided it by 4 lots of the sodium, and that got them an answer of 0.218-ish. So that showed you that you had less titanium chloride and more sodium. That meant that titanium chloride is the limiting reactant, because you would run out of that first. Okay? Happy to talk people through some of the other stuff on that if you want to learn a little bit more about it, but I generally find that you don't like me waffling too much about these quantitative chemistry ones and overcomplicating it. Okay? So I'll just let you pause it there if you want to look at the different approaches that you could do that's it's highlighted. And then I'll move on to 8.8. So it's saying here on 8.8 that 100% would have been 13.5, but they got 92.3. So what is that? So we get our 13.5, which is 100%. We divide it by 100 to find out what 1% is, and then we times that by 90.2.3 to find out what 92.3% is, which is 12.5, or however you rounded it, 12.4605, whatever. Doesn't matter in that case, because it's not asked for a particular number of significant figures. Usually only does that maybe once on an exam, so that you're not getting penalised for not knowing about significant figures more than once. And this should be our last question now. It's not bad going in 23 minutes. So the key words here are dilute and strong. Let's deal with the word strong first of all. So strong and weak are different to dilute and concentrated. Strong acids will completely dissociate, whereas weak acids only partially dissociate. When I'm saying that, I mean that strong acids like hydrochloric acid are made of hydrogen and chlorine. It will fully dissociate and split apart when it's dissolved into hydrogen and chlorine. Okay? Fully, there's no HCl joined together. So all strong acids completely lose their hydrogen ions to form a strong acid. A weak acid, it will have some of those atoms joined together still. So if we pretend for a second hydrochloric acid was a weak acid, some of the HCl's would still be stuck together. Not the case for this. The dilute bit is a bit that Mr. Diva and I had a little bit of a chinwag over and a little bit of a discussion, because we thought the mark scheme was tight here. So concentration is the like mass or moles divided by volume. So a low concentration, it's dilute because you've got a small amount of that acid per unit volume. That's where that definition answer has come from. People have said low concentration, and I had it marked right by me and Mr. Diva because we agreed that it's a bit tight, because a low concentration is correct for it being dilute. It has been watered down so that it is at a lower concentration, and it is a little bit tight to be so specific. Would you have got that right? Maybe not in the exam. If you appealed it, probably would. It would have been something I think that came up at a moderator's meeting where all the people marking the exams would have had a little bit of a chat about would it be fair to give the mark or not. 9.2. So pHs are in base 10, they're logarithmic. So if you get 10 times more hydrogen ions, then the pH decreases by 1. If you get 100 times more, it goes down by 2. They usually ask about it in this sort of a style, which is quite easy, because when you change that little indices, you are changing it by a factor of 10. So when you go from 10 to the minus 3 to the 10 to the minus 5, you've got 100 times less ions there, which means you will move along 2 places in the pH scale. So you will go from 10 to the minus 3 pH 3 to 10 to the minus 5 pH 5. Easier than it looks, hopefully. Oh god, speaking about easier than it looks. Right, titrations. Don't give up, first of all. You can get 2 out of 5 marks just by doing the average on this, which is marks you should not sniff at. So first of all, why is titration 1 not right? 23.5 is well away from the others. That is your rough titer. That is what you do when you don't know what the concentrations are, and you do it just to make sure that you will get a titration. So you open up the tap on your burette, pour it all through, and see at what point it roughly reacts. Because it's rough, we don't use it. We're going for concordant results, which means within 0.1 of each other. 21.1 is not concordant because it is well off. It's a whole milliliter, it's a whole centimetre cubed away from the others. So, first mark is for choosing 3, 4, and 5 for your average. If you don't get that mark, but you can still get a mark for doing an incorrect average. Add up those 3 and you should end up with 22.13. That's 2 marks. So before you do any of the really complicated stuff, there's 2 out of 5. Give yourself a pat on the back. That's decent scoring. Okay? Right. To work out the concentration of the sulfuric acid. So we know the volume of sodium hydroxide. We just worked out that's 22.13. We need to turn that into decimeters cubed because that's what the concentrations and stuff are in. We've got the answer at the end. So we divide it by 1,000, which gives 0.02213. That is where this bit of the equation comes in, where it's got the divide by 1,000. And we also know the concentration, because cheekily enough it's up here, it tells us that the concentration of sodium hydroxide, if you get the formula, concentration equals number of moles divided by the volume, and rearrange that to make the number of moles the term, you will find that you have to times the concentration there by the volume there, and that will give you 0.00232. Cheeky bit here, which makes this quite difficult in terms of a question. 2 sodium hydroxides react with 1 acid, which is why they've then gone, if there is 2 of the sodium hydroxides, we would need to half it for the sulfuric acid. So we've gone from 0.002 to 0.001. We've halved it. If you didn't do that step, then you'd lose 1 mark and get all the others as you're going through. Tough question. Really hard question. Use the same formula. Concentration is the number of moles divided by the volume. So we've got our number of moles here, and that 1,000 is sneaking in again because we want to convert that 25 milliliters or 25 centimeters cubed into 0.0025. That's how they've displayed it in this. So you can get 0.001162 divided by 0.025, and that should give you 0.0465. If you made a mistake and either doubled the numbers instead of halving them, or didn't spot that you should have been halving or the ratio or anything like that, then you could have got numbers like this, or like this, or like this, and you can score an appropriate number of marks related to that. Okay, tough question. 2 out of 5 is good. If you got 5 out of 5, hats off to you. You are fantastic at quantitative chemistry. It is unusual, but well done. 9.4. Mixed bag of answers here, and it's interesting to see what people were thinking. So you use pipette because it measures a fixed volume accurately. It does 25.0 milliliters or centimeters cubed, plus or minus 0.05, I think, at standard room temperature and pressure. Long story short, it does a volume way more accurately than a measuring cylinder or such. We use a burette for the other solution because we want to add that a bit at a time, and we need graduations. We need to be able to measure a range, so it needs to be variable. Okay, and our last one, 9.5. Quite a lot of people got 126 as an answer. And in that case, it's because you've not taken into account change in centimetres cubed into the decimeters cubed required. So that would be where the 30 divided by 1,000 comes from in this. What we're overall trying to do here, it's asking for a mass. We're given moles per decimeters cubed, so we need to work out the number of moles from the concentration and then turn the moles in using the Mr. Moles formula into a mass. So concentration is number of moles divided by the volume. To work out the number of moles, we were going to concentrate the volume times by concentration times by the volume. That's what this bit here is here. So that is 0.30 at 30 divided by 1,000 volume times by the concentration of 0.105, which will give us this number of moles, 0.00315. We're then going to use mass equals the Mr. Moles. So that is an MR of 40 times by the number of moles. So 0.105 times by 40 would give us 0.126 grams. Very well done again if you got that right, because remember you're using two formulas and you convert in the units and it's only giving you 2 marks. So that's a bit of a tight question. Last question on the test. Congratulations, that is some really tricky stuff and I have got some really fantastic scores for you. And I'm proud of what you've done. You've got a lot of time that you can make improvements on. Look at the scores that you got for each question. Find those weakest areas, and in the remaining bit of the lesson, if you've not been pausing, and how you've been going, you've got a chance now where you can get an Open National Academy or Seneca or something like that. You can go to that section and you can make some improvements. You can try some questions. You can revise some of that content. You can be looking at that over summer too. Okay. Now you've got good scores already on these mocks, and you can get better scores when it comes to your summer exams as well. So well done. I'm super proud of what you've done, and I look forward to continuing this stuff next year with you. Okay.